Hi all, this is lecture 25 on section 11.6, ratio and root tests. So in class we've been working on using limit comparison test and comparison test to find our convergence or divergence of series that kind of look similar to other series that we know about. But what happens if we start mixing things together, like part of a geometric with part of the one that looks like polynomials, and you get into some things that are a little bit tricky. Also, if you throw in n to the n and n factorial, it gets really tricky. So come to the rescue is the ratio test. So the ratio test shows, it helps us determine whether a series is convergent or divergent using the following rules. So we're going to look at the limit as n goes to infinity of the n plus 1th term divided by the nth term. Okay, so you're going to plug in your n plus 1, divide that by plug in your n, and we're going to look at that limit. And if that limit is less than 1, then the series is absolutely convergent. If it's greater than 1 or infinity, then the series is divergent. And if it turns out to be equal to 1, then our test is inconclusive, and we should probably go try a different test, like maybe limit comparison test or something else. Okay. All right, so let's take a look at how this is going to play out. So let's take a look at this one. So this is really an alternating series. So maybe alternating series test, but you can use ratio test here as well. So let's use the ratio test. And when we use the ratio test, we're looking at the limit as n goes to infinity of the absolute value of. Now we want a n plus 1 on top. So I'm going to plug in n plus 1. So that's negative 1 to the n plus 1 times n plus 1 cubed all over 3 to the n plus 1. And in the bottom, I want the original. So I want negative 1 to the n times n cubed over 3 to the n. And then I've got to simplify this. So the first thing that we're going to do is we're allowed to, because of the absolute value, get rid of the alternating term. Okay, so that just goes away. Then we want to deal with our improper fractions. So this is the limit as n goes to infinity, absolute value of n plus 1 cubed over 3 to the n plus 1 times, if we're dividing by a fraction, we multiply by its reciprocal. So this is times 3 to the n over n cubed. So flip it over. Now, what I want to do is simplify this so that I can cancel some stuff. So I'm going to make this, let's see, n plus 1 cubed is n cubed plus 3n squared plus 3n plus 1 all over 3n to the 1, n 3 to the n plus 1. I'm going to pull a 3 away so that I have 3 to the n and 3. That's the same as 3 to the n plus 1. And we're multiplying that by 3 to the n over n cubed. And the reason we do that is because now I can cancel that 3 to the n. I can also take this 3, which is in the bottom of the fraction, and bring it outside my limit. So this is the same as 1/3, because the 3's got to be in the denominator. The limit as n goes to infinity of n cubed plus 3n squared plus 3n plus 1 all over n cubed. Now, I can't just cancel that. I could divide it through if I wanted to, but I can't just cancel it. But I know what that is, right? That's the limit of a rational function for which the degree is the same on top and the bottom. So I just want the ratio coefficients for the n cubes, and that's just 1. So I end up with 1/3, which is less than 1, and so this is absolutely convergent. By the ratio test. Okay. Same thing down here. So we have n to the n and n factorial. So we're going to use the ratio test. So you look at the limit as n goes to infinity of absolute value of. Now you're placing n's with n plus 1. So up top you have n plus 1 to the n plus 1 all over n plus 1 factorial all over the original n to the n over n factorial. First thing we're going to do here is to multiply by the reciprocal. So we have n plus 1 times n plus 1 over n plus 1 factorial times n factorial over n to the n. Okay, our next job here is to simplify that first part so I can try to cancel some things. So I'm going to write this as n plus 1 times n plus 1 to the n, right? So that plus 1 in the exponent means I have a 1 that's multiplied. over. In the bottom, I'm going to pull an n plus 1 out of there as well. So if I pull an n plus 1 out of n factorial, that's n factorial. Because when you think about it, n plus 1 factorial is n plus 1 times the next number smaller than that is n times n minus 1 times n minus 2 all the way down to 1. So this is n factorial. Whoops, wrong side. So n plus 1 factorial is n factorial times n plus 1. And then I've got n factorial and n to the n. And now you can see that some stuff cancels. So first of all, there's an n plus 1 that cancels, and there's an n factorial that cancels. And that leaves us with the limit as n goes to infinity of n plus 1 to the n over n to the n. And this is the limit as n goes to infinity of n plus 1 over n to the n. And if I divide through, this is the limit as n goes to infinity of 1 plus 1 over n to the nth power. Now, this is an indeterminate form because 1 over m goes to 0, and then you get 1 to the infinity. And that's an indeterminate form, but we know that this one is special. This one is defined to be e. That is the definition of e. So our limit here turns out to be e. Now, e is 2 point something, which means this is greater than 1, which means that our series is going to diverge. So this is divergent by the ratio test. Okay. Now, next test is a root test. So anytime you have everything to the power of n, you want the root test, because the root test says instead of taking the ratio, taking the limit of the ratio, what you want is you want to take the limit of the nth root of your series. And if your limit is less than 1, then the series is absolutely convergent. Greater than 1, it's divergent, and equal to 1, it's inconclusive. So the same kind of results happen, or analysis happens at the end for both ratio and root tests. It's the same story. The idea is, are you taking a ratio or are you taking the root? So let's look at an example of that. So in order to take the root test, we're going to take the limit as n goes to infinity. And we're going to take our series, so 2n plus 3 over 3n plus 2 to the nth power, and we're going to raise it to the 1 over nth power. Essentially what that does is it takes off our n power. So this is the limit as n goes to infinity of just 2n plus 3 over 3n plus 2. And again, we have something that is polynomial over polynomial of the same degree. So we get the ratio of the leading coefficient. So this is 2/3. If you need to use L'Hopital's rule to get it, that's totally fine with me. And this is less than 1. And so this is absolutely convergent. By the root test. Okay. Here's another one. Example 2, we have something to a 5n power, and so we're going to take the limit as n goes to infinity of, we're going to take our series, n minus 2n. That looks like it shouldn't be that. I'll have to check on that one. That might be a typo. N plus 1 to the 5n, and we're going to raise it to the 1 over n power. Let me just quickly, I copied this from the text, and I probably typed it incorrectly. Let me see what I got. The n actually shouldn't be here at all. So this shouldn't be there. It's just negative 2n over n plus 1. Okay. Yep. All right. So what happens here when we're taking the root test is that we're taking the root of that. So 5n times 1 over n means that I end up with the limit as n goes to infinity of negative 2n over n plus 1 to the 5th. And we're allowed to take the limit of what's inside first. So this is the same as taking the limit as n goes to infinity of negative 2n over n plus 1 and raising our answer to the 5th power. That's one of our limit laws. And when I take the limit of what's inside here, this is equal to, let's see, this is a polynomial over polynomial. So this is negative 2. So negative 2 to the 5th is negative 32. Okay, all right, now looks like we missed something. What did I miss here? And we missed the absolute value. So we need absolute value here and here. In the first one, it didn't matter. Everything was positive. In this one, it does matter. And when we take the absolute value of 2 and take it to the 5th power, we end up with positive 32. And that's greater than 1, which means this is divergent by the root test.